Andy, what's your risk?
I don't know, but I probably don't want to find out. Last time we had like some
Good morning. So we got 3 weeks left. 3 weeks from today is our last lecture. I thought there'd be more cheering. I thought there'd be some cheering.
I mean, 3 weeks, that means there's a final after that. So
Yeah,
not really
well.
worth celebrating.
I'll celebrate when it's done.
Sorry?
I'll celebrate when it's done.
You'll celebrate when it's done. Yeah. Okay, so you're working on assignment number 3, and there will still be an assignment number 4, but you will not hand it in. Yep.
Just because there's a assembly problem on assignment 3, is assembly going to be on the final or not?
Yes.
Okay.
Yep. Assembly is a major part of the course. I'm going to talk about the final more in a while. Okay, but yeah. The final exam, I mean, anything we've done in the course is game on the final exam. Obviously, it's going to emphasize stuff that we've done since the midterm, but we'll talk more about the final exam as we get a little bit closer. As well, again, as I said about, what I'm going to do with the marks from the midterm. I'm mulling over some things. There's a few things we can do. So we'll talk about that more later on as we get closer to the final 2. Labs, some of you are still doing lab 4 this week. I think lab 5 starts next week, if I'm correct. Lab 5 is the last lab. I just remind you again that as per the course syllabus, you have to complete at least 4 labs to pass the course. So if you've blown off a lab somewhere already, make sure you don't do it again. You got to do at least 4 labs to pass the course. That's in the course syllabus. I mentioned it the first day. So please keep that in mind so that nobody has a nasty surprise at the end. But hopefully the labs have been not onerous. I don't think they have.
They do seem somewhat unrelated to the material.
They are, and I said that right at the beginning of the course. The labs used to be very related, and then Dr. Elnager, who took over this course in 2016, totally overhauled it. Well, he overhauled the lectures as well. And he taught it last year too. And he, when I was talking to him about it, he actually suggested, if I were you, I'd go back to the way you taught it in 2015, because the students certainly didn't like the way I taught it last year. I don't know what they didn't like, but that was his suggestion. So that's what I did. But I kept the labs. They are unrelated, but hopefully they are somewhat useful. If really the lab should be in assembly language, but the argument can also be made that so few people do assembly these days that, why spend a whole bunch of labs on it? So, okay, so labs, don't blow off the last one if you've already missed one, okay? Make sure you finish at least 4. Any other questions, comments? Yes, sir?
If so many people don't do assembly language, why are we learning it?
Because you need to know how a computer works. I mean, you took 248, right? How many people are going to do a triple integral after they walk out of here? Nobody, right? But you have to know these things if you're going to be an engineer. Otherwise, you go to tech school, right? Which I'm not putting down because I too went to tech school. And so I know the difference between tech school and university. In tech school, they teach you what you need to do the job, right? University, you got to know all the theory that enables the technology for the techs to do the job. So that's why we do it. Because this course is about how a computer works, right? And so knowing, at least having an appreciation for assembler is critical for knowing how a computer works. Okay, so what we're going to talk about for the remainder, we're going to talk about memory for 2, maybe 3 lectures, and then we're going to look at a little bit more on the hardware side, how things flow through a computer in order to execute these instructions that you've been writing in assembly language. And then finally, we're gonna look at pipelining, which is a very common method of improving the performance of computers. Okay, so memory. We're gonna look at RAM, we're gonna look at ROM, which probably everybody has heard those terms before. We're going to look at what's called virtual memory, and we're gonna spend a lot of time, well, a fair amount of time on cache memory, because it's very important for improving the performance of computers as well. But we're gonna start with RAM, which is random access memory. So let's just remind ourselves, if we're talking about memory in general, we're usually talking about a separate chip. Sometimes it is a physically distinct box from the processor. Sometimes it is a chip that is connected to the same bus. Often it's a chip that's connected to the same bus as the processor. So, and we have these interconnections between the processor and the memory unit, whatever that memory unit is. Okay, we have to, the processor has to supply addresses to the memory unit when it wants to access a particular memory location in that unit. That is a unidirectional bus, okay? The memory unit never has to send an address back to the processor. It's the processor always sending an address to the memory. Whether it's a read or a write, it's the processor telling the memory unit where that operation is going to happen in the memory unit. The other two major buses are bidirectional. Obviously, we need to be able to send data from the processor to the memory, and we need to send data from the memory unit back to the processor, so that's bidirectional, as are the control lines. Most of the important control lines are going, or most of the important control signals are going from the processor to the memory unit. For instance, a read-write line, which is basically telling the memory unit whether we're reading or we're writing to a memory location, okay? These buses are not just a single wire or a single trace on a PCB. They are a number of wires in parallel. And for instance, if we have K lines on our address bus, that means we have 2 to the K addressable locations, right? Because each one of these lines is carrying a 1 or a 0. So the address space of your memory unit is dictated by how big this address bus is. Same with the data, right? We've got a number of parallel lines here on the data bus, 1 per bit, and therefore if you have, you know, a 16-bit data line, well, that means you can send a word of 16 bits wide at one time over that bus. Okay, and these control lines, there's just 1 per functionality. So those are the connections we have. So RAM is what we're going to talk about first, and everybody's heard of RAM. If you've ever bought a computer, you've seen the word RAM, which stands for random access memory. And really the defining attribute for RAM is that any location in the memory unit, whether you're reading or writing to it, can be accessed in roughly the same amount of time, okay? Doesn't matter where that particular location is in memory, it takes about the same amount of time to read and write to that location as any other location in that memory unit. Yeah?
Is reading and writing also the same amount of time, or is it just that all needs to take the same amount of time?
It's going to be a little bit different between reading and writing because, you know, you've got different latches on the processor side than you might on the memory unit side. They might have a little bit of a different time to latch data in. It's pretty close though, I think. It's not that different. Okay, so this might seem obvious, you know, why make this distinction? Well, RAM is a term that has been used for decades, and before there was electronic memory, there was, you know, mechanical memory. If you look at computer history, sorry.
Punch cards?
Punch cards, even going back further than that, memory used to be wires with beads at the connection, at the crossroad of 2 wires. And you would actually magnetize this metal bead, or not, to store a 1 or a 0, okay? Very soon after that, though, you've probably, if you've ever watched an older movie and there's computers, there's sometimes a tape drive, you know? Everybody know what a tape drive is, right? I mean, those were used for decades, right? And that would not be RAM, because obviously some piece of information on one end of the tape it would take longer perhaps to get to it than some other piece of location, a piece of data on a different location on the tape, right? The tape's got to wind really fast to find that place and that piece of data. That's a good counter example for RAM, right? It takes different amounts of time to access data on a tape drive than it does in what we call RAM. Yeah?
I'm assuming a hard drive is not considered that because you have to move the needle.
Exactly. A hard drive is a more modern counter example to RAM, right? Because it's an actual disk, and you know where a piece of data is on that disk, it might take more time or less time compared to a different location on the disk, because something has to be moving.
The solid state drive would be closer to RAM.
Yeah, that's not, a solid state drive would be closer to RAM, not,
Not as
Closer but
fast.
not included.
I don't know if you would call it that. RAM is, yeah, I don't know. That's a distinction
Are they
I've
not
never
the
made.
same architecture though?
I'm not
Solid
sure
state
about solid state versus RAM, no.
I was just really reading about life on solid state drives, and apparently it's handled very differently.
Okay, thank you, yeah.
Maybe NVMEs are closer.
So when we're talking about RAM, we're talking about the electronic type of memory cells that we've been using in computers for quite some time. And we're gonna look at how they're kind of set up and what a basic cell looks like that holds a bit of 1 and 0. Okay, so RAM as opposed to ROM, which we'll talk about next. Ideally, we want memories to be large, fast, and inexpensive, right? We want everything. We want to eat our cake and still have it too. But really, these are competing objectives when it comes to memory. Larger memories are typically more expensive. Larger memories obviously take more power. Larger memories usually are slower as well. Almost always are slower as well. Okay, so having fast, power effective, large memories, you can't really do that, right? There's always this trade-off between these different attributes of memory. So we're gonna look at two basic types of memories, and there's, you know, in the years that have gone by, there are variations on these two. The technology is constantly evolving, obviously, but we're gonna be looking at these two, SRAM and DRAM, okay? And SRAM is typically more expensive memory, and because it's faster, it takes less power, but also it's less dense, so it's not as big, okay? Whereas DRAM is cheap. And DRAM is typically what, you know, when you go and buy a new SIM card for your computer, and nobody really does that anymore, but when we used to, when we'd have these big DOS boxes, you pop the cover off, you slap another SIM card in, that's typically DRAM. It's cheap, it's very dense, so there's lots of memory on a single chip, but of course it's much slower, okay? So we're gonna be looking at those two different types.
It's something you stick in your phone.
Couple of terms that are important when it comes, yep.
Did you mean SD card or SIM?
No, SIM is SIMM.
Oh, okay.
That's coming later. See, you guys don't even know about SIM cards because you haven't had to do that with your computers. It's different than the SIM card you're talking about. Sorry. SIMM, not SIM. So a couple of terms when it comes to evaluating the performance of memory. Memory access time, okay? Even though it's all electronics, and we always think electronics are working at the speed of light, it's not quite so. It's a little bit slower than the speed of light, and the circuitry takes time to operate, okay? So even though you're talking about nanoseconds, it's still not instantaneous. It still takes some finite amount of time to read a data value from a memory or to write a data value to a memory. Okay, so the time it takes to do that kind of operation is what we call memory access time. And obviously we want that to be as short as possible. There's also what we call a memory cycle time, okay, which is the time between operations. So if you write something to a memory unit at a particular address, and then you want to write another data value to a different address in the same memory unit, you can't do it right after the first write operation. There has to be some amount of time. And again, that has to do with the different circuitry, the latches, the flip-flops. They have to be at certain values for a certain amount of time to work properly. So memory cycle time, but obviously we want that to be as short as possible as well. So when you're looking at different types of memory, you'll see these terms used. And obviously we want those numbers to be small. Okay, well, before we look at an actual RAM cell, let's look at how RAM is organized, okay? And we're gonna look at a very small example. Obviously, the RAM chips that we have these days are much bigger. There's way more cells in them than what we're gonna look at, but for ease of understanding, we're gonna be looking at relatively small memories. For instance, 128-bit memory, okay? So this block diagram here represents 128 bits in memory, and they can be organized in a number of different ways. We're gonna start by looking at a 16:8 memory, okay, which means we have 16 words, 8 bits each. Obviously, 16 times 8 is 128 bits. Okay, there's different ways this 128 bits could be organized, but typically we organize them in terms of words, okay, rather than one bit at a time, although you can do that as well. So in these block diagrams, these little boxes here correspond to an individual memory location that can hold a 1 or a 0. Okay, each one of those holds a bit, and we have bit lines that come off or out of that cell, okay? There's always 2 bit lines. If this cell currently holds a 1, then the bit line, say B7, would have a 1 on it, and this would always be the opposite, a 0. Or if the cell is holding a 0, well then this side will have a 0 on it and this side will have the 1. Okay, you have always access to the real value and its inverse, okay? So these bit lines are connected in parallel with all the other bits. For instance, this would be the first bit in each of 16 words. Okay, so this is a 16:8, so we would have 16 rows here of 8 bits each. And the first bit in each word is going to be, these bit lines are all connected together because we're going to read one word at a time. Okay? And these two bit lines, I forget the word they use in the textbook for this, but the real value and its inverse will go to what we call sense-write circuits. Okay, so there's circuitry in here that can either sense whether this is a 1 or a 0, or it's got an amplifier in it, which will then send a value onto this bit line to actually write a value into one of these bit cells. And then obviously on the other side of that is the actual data lines for this memory chip. Okay, so this memory chip would have 8 data lines because one word is 8 bits long. So you can read out 8-bit values corresponding to one of these rows at a time. Okay, on the other side here we have what we call the word lines. Okay, and these word lines will activate 8 particular bits in one of these words. And on the other side of this are our address lines. So these are the external connections to this memory chip, right? We would have 4 address lines because 2 to the 4 is 16. That will allow us to access or address one of these 16 rows at a time. Okay, so if we choose, if the address line is 0000, that would choose this word up here, which would activate this word line, which would activate these, and that would tell this cell, put your values out on the bit lines. Or they're always there, but it would no, they're not always there. I should say they connect these values to the bit lines, whereas all of these will not be connected to the bit lines, right? And there's circuitry in here that does that. Yep.
Essentially an AND gate?
I think it's more than an AND gate. I know down here they use, what do they call them? Tri-state. I'm not sure if that's what they use here. Okay, so you only activate one word at a time based on the 4 bits here in the address. When you activate this word, the values of those 8 bits are placed on the bit lines, are sensed by this, which then will latch them out to these 8 external data lines. Conversely, if we wanted to write to this first word here, well, you put the address 0000 on the address lines, you would put the corresponding data that you want to write there, and then you have to tell this chip that you actually want to write instead of read. And we use this control line here to do that. So this is one of the control lines on the control bus between the processor and the memory unit, the read-write. So if this is set at a high, that's telling the memory chip here, we want to read a value from here. Okay, so that means when you put the address here, these values are going to, say for this row, these values are going to hit these bit lines, and this sense write circuitry is then going to send that out on the data lines. If we're writing instead, this would be a 0, which means take the data that's coming in here, put it on the bit lines, and that will be written into these cells if this address is 0000. Yes, sir?
So the words are going horizontally across on this.
Yes, one word is like that. Is like a one word is a row.
And so when you say you want to like write, you say that the address line will be 0000.
If I want to write to this first word here.
Okay, but if the word is 8 bits, like you have an 8-bit word, how come you don't need 8 bits of like wires, 1 bit going each?
These are the 8 data lines down here.
Okay, so on the left there, that's not.
This is the address.
Oh, okay.
This is the address. And because there's 16 words, we need 2 to the 4. We need 4 bits for our address because 2 to the 4 is 16.
Yeah.
Okay? Yes, sir.
Should it be assumed that every single one of those bit cells has a read-write line of its own then, which the controller is?
No, it's this sense write circuitry that controls whether reading or writing is happening here. The only other thing we haven't talked about here is the CS control line, which is chip select. Because presumably you have more than one memory chip that this processor is connected to. Okay, so these address lines would be connected to all of the chips, all the memory chips, right? And the processor needs to be able to choose which memory chip it's asking that address from. So we would have this chip select line here. When this is active, okay, then everything here will work and data will be able to hit the data bus. If this is inactive, that means this chip is not being used, and this effectively isolates the data lines from anything going on in here. Yes?
All right, back to my previous comment. How does that work then? How do the cells know to take data instead of give data? If the sense write circuit is what's controlling that?
Yeah, there's some sort of latches on the end of these. I don't know what they are, to be honest. The sense circuitry is reading and putting data on here. And again, it's this word signal which is activating whether this is connected electrically or not. It's always physically connected, obviously. But yeah, there's some sort of circuitry or latch here which is going to be activated by this word line. If this word line is active, well then the data values in here is going to be electrically connected to those lines. And if this is not active, there will be no electrical connection there. Okay? So this is, we're going to look at 2 or 3 of these, and they're all kind of the same like this. But this is one way in which it can be set up. And again, it's very common that it's done in an array fashion like this. Okay? Length of word and bit lines have a big impact on power and speed. Obviously, the more of anything you have, the more power, because there's circuitry here everywhere. The more of these you have, the more power you need. And of course, as it becomes bigger, it becomes slower. Okay, like a whole lot of other things in the world. Here, this is going to be on an integrated circuit. You need a number of pins in order to connect it to the outside world, right? You're going to need 4 address pins. You're going to need 8 data pins, so 4 plus 8. And we're going to need at least 2 control pins here, right? Read, write, and chip select, plus power and ground, which we don't show here. Okay? All right, so in this particular 128-bit chip, we have 128 storage cells. If we organize it like a 16 by 8, we can figure out how many pins we need. If we go back for this particular, we would need 4 address lines, 8 data lines, 2 control lines, read, write, and chip select, and then power and ground. So we'd need 16 pins. Obviously, if we have a bigger memory cell, we're going to have more pins, more data lines and address lines in particular. We could also change the way we organize the memory. So let's say we were looking at 1,024 cells, so a 1K chip instead of 128 bits. Well, we could organize that as 128 words, again, each 8 bits wide, okay? Because 128 times 8 would give us 1,024. In that case, we again need 8 pins for our data lines, so 8 pins for our data lines. For 128 words, we need 128 addresses. So that means we need 2 to the 7, or 7 address pins, right? Because 2 to the 7 gives us 128 addresses. So we need 7 address lines, we need 8 data lines, again, 2 control lines, read, write, chip select, and power and ground, so we would need 19 pins for a 1K memory unit organized as 128 by 8. Or you could say, well, instead of having a word be 8 bits, I'm going to have a word just be 1 bit. Okay, so I would organize that as 1,024 words, each 1 bit wide, instead of 8 bit wide. Okay, it gives you the same number of memory cells, 1,024, but organized a little differently. Well, how many data line, or how many pins would we need now? Well, again, 2 for power and ground, 2 for chip select and write. Now we need only 1 data line because our word is only 1 bit wide. But we would need 10 address lines because 2 to the 10 would give us 1,024 addresses. Okay, so this would be only 15 pins as opposed to 19 pins. Same number of memory cells but fewer pins. But of course, what's the trade-off?
Slower read time?
Slower read time because
You have to read 1 bit at a
you're
time.
only reading 1 bit at a time, right? Obviously. So yes, fewer pins, which means lower cost, but your word is only 1 bit as opposed to 8 bits, and so you're only reading out 1 bit at a time as opposed to 8 bits at a time. Okay. But you know, in certain applications, maybe you only need 1 bit at a time, depending on what it is. So in a case like that, you might want to consider using a 1,024 by 1 versus 128 by 8. The point is, the way you organize the cells has an impact on the number of pins, which is of course cost, but it also has an impact on performance. You could also use a 32 by 32 array and divide address bits to have 5 upper bits for row, and so 32 by 32. That's more than 1,024. No, that is 1,024, right? Yeah, 30 by 30 would be 90, yeah. So if we had 1,020, another way we could organize that 1,024 bits is to have 32 rows of 32 bits, okay? So now we need fewer addresses. We only need 32 addresses, so we need fewer address lines, but of course now we need 32 data lines, okay? But there's clever things that we can do. We can do multiplexing on the address bits where we could use fewer address lines. And for instance, if we have 32 by 32, that means you have 32 rows and 32 bits per row. So something we can do is we can reduce the number of data lines simply by choosing just address lines, just by choosing 1 word. And then if we wanted to choose, say, 1 bit within that word, well, we don't have to use all the address lines to choose 32. We can multiplex, and we'll look at an example of this later on, okay? But there's clever things we can do to reduce the number of pins. And one of them is multiplexing the address lines, using the same address lines to, for instance, specify a row and a column if you're not going to read the whole row at once. Okay, we'll look at an example of that right here, for instance. So if we want a 1K by 1 memory, so we'll go back to 1,024 memory cells, okay, we can organize that as a 32 by 32 memory cell array. So 32 rows, 32 bits per row gives us our 1,024 bits. Okay, so we need our we need our 32 bits to give us our address here. Let's go back here. Let's start at the outside. So a 10-bit address, because 2 to the 10 would be, anybody know? 1024, right? We want to specify one of these 1024 bits inside of here, okay? We're going to address only one at a time. So we need 10 bits, a 10-bit address, because 2 to the 10 is 1024. So 5 of those address lines are going to choose, if we organize our memory like this, 5 of those address lines are going to choose one row. The other 5 address lines are going to choose one column, because 2 to the 5 is equal to 32, right? And we have 32 rows of 32 bits each. So we can take this 10-bit address, and 5 of those rows are going to choose one of the 32. 5 of those bits are going to choose one of the 32 rows. The other 5 bits are going to choose one of the 32 columns. And that'll give us one particular cell here, one bit that will be addressed by this. Okay? So this is how it could be shaped like this. And they often do this to maintain a square shape, which has advantages, I assume, for manufacturing. Okay, so, and obviously we're using some pretty big block diagrams here that do a lot of different stuff, right? This here, output, the 32 to 1 output multiplexer and input demultiplexer is going to take these 5 bits on the address, which correspond to one particular column, one of the 32 columns. Obviously, that's going to activate one of these sense write circuitry units for that particular column. And obviously, that has to go then out our single data line, because we're reading one bit at a time. And we need the read write and the chip select as well. Okay? So basic concepts of how the memory is organized. Okay, so the memory units themselves, so what will they look like? Well, here we're going to start looking at the 2 different basic types of RAM. Again, there's variations on these as technology has evolved. But basically, the first type we look at is what we call SRAM, which stands for static RAM, okay? And static RAM, because static means, you know, stationary or it stays, it retains its state as long as power is applied. As long as the ground and power to that RAM chip is there, those values in those cells remain, okay? Static RAM. However, we say they're volatile, and maybe you've heard of memory being volatile. Volatile just basically means if you turn the power off, everything's gone, right? Which is why when you start up your computer or you boot up your computer, it's got to load the operating system into the RAM, or it's got to load some stuff into RAM, right? Because when you turned off the power, everything in RAM goes away. Everything in SRAM goes away, okay? So it's volatile. Okay, and a basic SRAM circuit cell looks like something like this. It holds a 1 or a 0. It basically consists of 2 inverters and 2 transistors. So the transistors, you know, getting to the previous questions, it's relatively simple circuitry. These transistors are just going to electrically connect these 2 points when that transistor is turned on, or it's going to electrically disconnect these 2 points when this transistor is turned off. And so the base of these transistors is connected to your word line, right? So you activate this word line, you turn on these 2 transistors. Now this point is electrically connected to X, and this point is electrically connected to Y, okay? And either that means that if we're sensing, if we're reading this cell, these values will show up here, and then the sense write circuitry down here will determine what those values are, or if we're writing to that cell, well then the sense write circuitry is actually going to force this line high or low, which will then force this to high or low if this transistor's on. Okay, and the inverters, obviously, the way they work, if X is at a high, Y is going to be at a low. It's the opposite. And if Y is at a low, X is at a high. Okay, so that's a basic SRAM cell. Yeah, and this is what we just talked about. So you activate the word line here, turns on the transistors. Now these 2 points are connected, and these 2 points are connected. Okay, so a read operation and a read operation is exactly the same, except now the sense write circuitry connected to the bit lines is going to force these bit lines to a particular value. For instance, if we want to store a 1 here, it's going to force this bit line to a 1, right? Again, T1 and T2 are turned on because this word line has been activated, so this 1 drives X to plus 5 volts, which will force this to 0 volts, if we're talking about TTL technology. And so it'll set this to 5 volts, set this to 0 volts, the sense circuitry, which will then set X and Y accordingly. Okay, and that obviously will stay there while power is applied, because these inverters obviously need power. Okay. So how are those inverters often implemented? Well, they could be implemented with CMOS technology. I think you guys have probably seen CMOS yet? No, not yet. Okay, you're going to be taking microelectronics next term, maybe? Next term? You'll see CMOS along the way. It's a particular technology for circuitry. Complementary metal oxides semiconductors, I think is the right acronym. And basically, we can implement these inverters just using transistors. When you're making a VLSI chip, a very large scale integrated chip, the best way to do that obviously is to just put as many transistors as you can on there. If you need different types of components, obviously that gets harder to manufacture. If you can just, like an assembly line, just punch a billion transistors onto this chip, that's the way to go. So we tend to implement as much circuitry as we can, for instance, with transistors. So these inverters could be implemented like transistors. So this inverter A here could be implemented by a pair of transistors, T4 and T6. B here by these 2 transistors here. But it works the same way. Notice that these 2 transistors are different active inputs on the base, right? To turn T5 on, you need to put a 1 here. To turn T3 on, you need to put a 0 here because of the bubble, right? The bubble means inversion. And same thing here and here. So if we look how it operates the same way. So for instance, if this cell is holding a 1, which means we've got plus 5 volts here, if we turn on T1, that means plus 5 volts or a 1 at X, which would mean a 0 at Y. So if you have a 1 at X, well, that 1 would turn T6 on, correct? If we had a 1 here, X is connected to the base of T6, so that'll turn T6 on. And the 1 here will turn T4 off. So if we got a 1 here at X. Okay? Now if T4 is off and T1 or T6 is on, well, here this is, let's call this the emitter of T6, is connected to ground. So when you turn T6 on, that means Y will be at ground, or 0. Okay? And because T4 is off, obviously we'll have, if V supply is 5 volts, we'll have 5 volts across the base or the emitter and collector of, I should have called this the emitter and this the collector, right? Doesn't really matter. When T4 is off, these 2 are not connected electrically, and therefore you'll have this V supply on this side, you'll have ground on this side, that's all good. This will be on, you have ground all the way here, connection to ground like this. Okay, on this side over here, so if we've got a 0 here now, that 0 will turn T5 off. Right? And that 0 will turn T3 on because of the bubble here. It means this is active low. So T3 is turned on. So if T3 is turned on, then that means this 5 volts here appears at X, which gives us a 1. This is off, so we've got 5 volts on this side, ground on that side, that's okay. Okay, so that would be currently holding a 1. And obviously 0 and 1 the other way. Okay? So that's how we could implement a simple SRAM cell. It would require 6 transistors. Okay. And I think this is what we just talked about. Yep. And obviously the same thing, T1 and T2 are turned on by this word line. If this is set to a high, these are on, and the voltage at X appears here, the voltage at Y appears there. If you're reading. If you're writing, again, you turn T1 and T2 on, and now the sense write circuitry connected to these bit lines will force, for instance, B to a high if we want to write a 1, and it'll force B prime to a low. If this gets forced to a high, well then X gets forced to a high. This high here will turn this T6 on, will turn T4 off, which will force this to be a low. This low will turn T5 on, which turns, will turn T3 on, and that low will turn T5 off, which will then force this to be 1, which reaffirms or reinforces the bit line driving that to a 1. Okay? And then obviously once that's once the operation is over, the word line is deactivated, but X and Y will retain their states. Okay? Any questions about a basic SRAM cell? Okay, advantages and disadvantages of SRAM. SRAM is fast, okay? Very fast access time, so the time to read something from memory or write something is around 15 nanoseconds, maybe even quicker these days. And it requires very low power because current only flows when the cell is being accessed. Okay? The disadvantage is we need 6 transistors for 1 cell, which means, you know, you can only get so many transistors on a chip, so that means you can have only so many cells if every transistor needs 6 cells. So it means low density. So SRAM is expensive, it's not very dense, so it's small, but it's low power and it's fast, okay? So where do we use it? Well, for instance, the internal registers on your processor, right? The ARM processor only has 32 internal registers. You don't need a lot of them, but you want them to be fast because every instruction basically uses registers. So you want to make your registers SRAM. We're going to be talking about cache a lot in lecture 2, and cache is memory that is specifically intended to be used often, and therefore you want it to be fast as well, but we'd like it to be as big as possible, but more importantly, we want it to be fast. So we typically use SRAM for cache memory as well. FPGAs, which have limited memory as well, and the main memory for smaller embedded applications, right? Perhaps the computer in your refrigerator, right? It doesn't need a lot of memory to do what it does, so you might use SRAM for that because it's fast. Okay, so that's SRAM. DRAM is the second type of memory we want to look at, which is called DRAM because it stands for Dynamic Random Access Memory. It does not retain its state indefinitely. With SRAM, we called it SRAM because it's static RAM. As long as there's power applied, those cells will hold their state forever, okay? You don't have to you can write a value to it, leave it alone, and it'll stay like that for a long time. Obviously not forever, but for a long time. Dynamic RAM won't do that because of the way the cells in dynamic RAM are constructed. They leak, okay? They leak because a capacitor is involved. And even though you charge up this capacitor, over time, it's going to discharge through the dielectric. So even though you set this cell to, for instance, hold a 1, which means charges capacitor up to 5 volts, if you do that and then leave it alone, eventually this capacitor, the voltage across this capacitor will go down to 0, okay? And so you have to periodically refresh it. So it's dynamic. It doesn't stay static. It changes over time. It discharges, and you have to refresh what this cell holds periodically. Okay, that is typically done during a read operation, because when you read, when the circuitry is reading the value of the cell, it's the same way. We've got a word line and we've got a bit line. You activate this word line, it's going to turn on T1, which electrically connects this capacitor to the bit line. Okay, so when we're reading whether this capacitor is charged or discharged, you turn on the word line, and then the sense write circuitry is going to detect, well, is there 5 volts here or is there not 5 volts? Is it like 0 volts? So it reads that value. If it reads 5 volts, it will then drive this bit line up to a full, well, let's say it reads 4 volts because this capacitor is discharged a little bit. The sense write circuitry will detect 4 volts here. When the word line's activated, it'll go, okay, there's a 1 stored there, and I'm gonna charge it from 4 volts back up to 5 volts. I'm gonna refresh it. Okay, so that's automatically done by some circuitry up here when it reads the value of this cell. If this capacitor is currently at 0 volts, or maybe for some reasons it's at negative 1 volt, okay? Again, the sense write circuitry is going to sense that. It's going to go, oh, okay, negative 1 volt, that's a 0. And then it's going to apply a voltage here in order to charge this capacitor to 0 volts. Okay, so it's going to refresh it back to 0. So it does that every time it reads, and if you don't read the cell often, that's going to have to happen periodically by some other mechanism, which we'll talk about in a second. Okay, so typically the value is only maintained for tens of milliseconds. Okay, so these little tiny capacitors, and they are extremely small, they're on the integrated circuit, they leak quite a bit, quite quickly, and they lose their charge really fast, right, because they're so small. So they need to be refreshed very quickly, every tens of milliseconds or so. So that's why we call it DRAM. But of course you can see why DRAM is generally what used for large memories, right? All you need to implement a DRAM circuit is 1 transistor and 1 tiny little capacitor. So the cells physically are very, very small. So you can pack a whole bunch of them onto a circuit, onto an IC. So the advantages and disadvantages, well, again, it's cheap, right? 1 capacitor, 1 transistor, that's all you need, and it can be very dense. You don't need a lot of components for each cell. The disadvantage, well, the transistor is constantly leaking, this transistor here, so it's wasting power, so they tend to be a bit power hungry. It, like we said, requires constant refreshing, so that has to be done. And the access time is relatively slow as well, which you might ask why, because it's just 1 transistor here, but I'm thinking it has something to do with the refreshing as well. Okay, because when you read, the circuitry also has to refresh, which of course will take some time. So they're a lot slower, 60 nanoseconds to access memory as opposed to 15, for instance, for an SRAM cell. So they're bigger, more power hungry, they're slower, but they're very cheap, okay, which is their main advantage. Where would you use these? Well, this is typically the main memory that we use in our computers and for slower embedded applications where you don't need really a lot of speed, so you don't want to spend money on SRAM. Yes, sir?
I'm assuming that those are also volatile then?
Yeah, you turn them off and they're gone. Yeah, because if they don't get refreshed after a few milliseconds, it's gone, right? Yeah, exactly. Also volatile. Okay, so in the time we got left, let's look at least at this one. So we're going to be looking at 2 types of DRAM, asynchronous and synchronous. And basically asynchronous means there's no clock involved, whereas synchronous DRAM uses a clock signal. We'll talk about those next day. So for instance, if we want to look at a 256 megabit DRAM, well, we could configure that like this. So 32 mega words, where each word is 8 bits. Or you can think of it as 32 mega rows. No, that's not how this cell array is configured, so I shouldn't say that. 32 mega words, where every word is 8 bits wide, okay? So this particular DRAM chip is organized like this. It's got 16,000 or 16K rows, and each row consists of 2K bytes. Okay, so we've got 16K rows, and in each row, there's going to be 2,000 times 8 bits. Okay, so basically 16K bits. And those 16K bits are going to be organized into bytes. Okay, so that means there's 2K bytes in each one of these 16K rows in this cell array. Sometimes the hardest part when you're looking at these diagrams is keeping in mind what the cell array actually looks like, okay? Okay, well, just like in the previous example, for each one of these 16K rows, we need to have an address to specify which row we want to look at. Okay, so we need a row decoder, which means some of these address pins are going to be used for the row decoder to specify one of these 16K rows. How many do we need? Okay, well, we have our address lines here going from 0 to 24, which means we have 25 address lines. So can somebody do 2 to the 25? Anybody got a calculator handy? 2 to the 25? Anybody know what that is? $33,554,000. 32 million?
33 million.
33 million. So basically 32 meg here.
Yeah.
Right? So these 25 address lines are going to specify one of the bits here. Should I say bits? I shouldn't. You said 33 million, right?
Yeah.
But this is a 33 or 32 meg by 8. So this address, the full address, is going to specify 1 byte in this cell array, right? Because we've got 32 million bytes in this memory. So 2 to the 25 gives us 32 million addresses. That specifies 1 byte in here. To get one particular byte, we need to specify its row, and then we need to specify one of the 2,000 columns, because there's 2,000 bytes in each row. Okay, so that's why we divide the address bits up into, again, some of these bits are going to be used to specify which of the 16,000 rows we want to activate, and then the rest are going to activate the bit lines for one of the 2,000 bytes in that row. Okay, so some of these addresses are going to be latched into what we call the row address latch when this signal is activated. This is the row address strobe signal. So when this goes low, it's going to be 0 to 10. We need more for 0 to 10, 11 to 13. We're going to need these address lines are going to be latched into the row address latch, decoded here, and are going to activate one of the 16,000 rows. These are going to be latched into the column address latch when this strobe signal goes low, which is the column decoder then is going to activate the 8-bit lines for one of the bytes in that particular row to either read or write. Okay? Okay, we'll continue talking about that later. Sorry to keep you late.